Recall when we were examining the motion of an object in 2 dimensions, we introduced a Cartesian coordinate and a position vector. Now, let's suppose the object has moved to a new point along the orbit. Well, we'll write another vector, r of t, and let's say this took a time delta t to the new point. And what we want to define is the displacement of that object. So that's a vector delta r. And recall that a vector at time at t plus delta t is equal to the old vector r of t plus this displacement vector delta r. Now, what we want to consider is a limit as delta t goes to 0. And let's just look graphically at what that means. As we move this delta t, as delta t gets smaller and smaller, and our object is getting closer and closer to its position at time t, and the position vector r at t plus delta t is getting closer and closer to r of t delta t, the key fact is that if we drew a tangent to the orbit, then the limit of delta r is approaching tangent to the curve. So in the limit delta r, the direction is tangent to the orbit. So that's our first key property of delta r. Now, the second thing we want to express is if we write delta r as a displacement in the I hat direction and a displacement in the j hat direction. Now, again, maybe we can just clean this up a little bit and see what we mean by that. So here's our delta r. And we have a little delta x in this direction, delta y in that direction. Remember, delta x or delta y can be positive or negative. That's all right. Now, if we want to define our velocity as the limit as delta t goes to 0 of delta r over delta t, then what we see is we have two pieces, the limit as delta t goes to 0 of delta x over delta t I hat, plus the limit as delta t goes to 0 of delta y, delta t, j hat. And the definition of these limits, we'll write that as the derivative dr dt. So the velocity is dr dt, and that's equal to dx dt, how that coordinate function is changing in time, I hat, plus dy dt j hat. Now, as far as notation goes, we write this velocity as an x component of the velocity plus a y component of the velocity, where the x component vx is dx dt, and the y component is dy dt. Now, recall that the direction was tangent to the curve, but the magnitude of the velocity, what we call the speed, is just the sum of the squares of the components, the square root. And so now we've described what we refer to as the instantaneous velocity. So far, we've looked at a trajectory in 2 dimensions. Let's again consider some type of motion where we choose a positive y-axis, a positive x-axis, an origin, unit vectors, I hat and j hat, and we'll have some type of trajectory where our object is moving like that. We know that at this particular time, the velocity is tangent to this trajectory at that point. And now what we'd like to do is try to describe, we've described its 2 components, vx and vy, as a vector. So if we did vector decomposition, we would write a vector like this and a vector like that. This is the x component. That's the y component. And now if I define this angle theta, We know that a vector has a direction and a magnitude. We've seen that we call the magnitude the speed. So that's just the sum of these components squared square root. Speed is always positive, so we always take the positive square root. And now what about the direction of this vector in the xy plane? Well, we can see from our geometry that the tangent theta is given by the y component over the x component. Or one could say that the angle theta at this given time is the inverse function of Vy over Vx. And so now we've described not only the direction of the velocity, but the angle that it's making with the horizontal axis. And so we've now completely described the velocity, instantaneous velocity vector at time t in terms of its two component functions, its speed, and the angle that it makes with the positive x-axis.